Welcome to the last week of lectures. And in this very last bit of lectures, we will provide a super brief introduction to the EM algorithm. As I have said, this is going to be a brief introduction, so you might need to take a more advanced class if you want to learn more about the theory and more advanced implementations of EM. First, let's try to recap what we talked about last time. So last week's lectures were on optimization. We saw how nonlinear optimization may be used to numerically compute the maximum likelihood estimate, or the MLE, of the unknown parameter theta based on the observed data x. This was done by minimizing the objective function, which is the negative log likelihood of theta. The negative log likelihood of theta is denoted by negative L of theta given x, and this is equal to the negative of the natural log of the joint density of all of the data given the parameter theta. When all of the data is observed, so when we observe all of the values of x, then we can plug all of the x's into the negative log likelihood. And the only remaining variable in the objective is theta. In this case, finding the optimum is quite straightforward. For example, using the Newton-Raphson method, or computing the derivatives first and then implementing unit root to find the 0 points. Or we also talked about using the built-in function optim inside R. However, a common complication in statistics occurs when not all of the data are observed. As you can imagine, when some people complete surveys, some questions are not going to be responded by all examinees. In this case, part of the data are going to be missing. Another example is when there are unobserved latent variables. For example, in a mixture of two normal distributions, the unobserved membership of an observation can be considered as a latent variable. So the membership stands for whether an observation comes from the first normal distribution, group 1, or the second one, group 2. As you might remember, that's how we generated the mixture normal data. So the membership of individuals determine which normal distribution they come from. However, this is not something we can observe from the data because we just observe the mixture normal observations. Another example of latent variables is related to my research. So when I do psychological tests, as you can imagine in a personality test, people complete a set of survey questions. Each question might be a Likert scale question where it asks people whether they agree or disagree with some statement. So the unobserved personality trait value of a person, for example, the degree of extroversion or introversion that they have, it's something that we cannot directly see. However, it governs the person's responses to all questions inside that questionnaire. In this case, we have the data where part of this is observed, such as people's responses to questionnaires, or such as the x values that we observe from the mixture normal, and part of the data that is missing, such as people's latent membership or their latent trait on some personality. So if we partition the data into two parts, the observed data and the missing data, then the likelihood given the complete data, that is all x's, is L of theta given x, and that is still the joint density of all of the data given theta, and that's equal to the joint density of the observed data and the missing data given the unknown parameter theta. You can also write this as the marginal distribution of the observed data given theta and the conditional distribution of the missing data given the observed data and theta. But note, in reality, we do not observe the complete data. We only observe x-ops, and we don't have this part. One question you might have in this case is how do we find the MLA for theta when we do not observe X miss? Because we don't observe this part, inside the complete likelihood, X miss is also unknown, and theta is no longer the only variable left. Well, one straightforward option you might think of is let's maximize the observed data log likelihood. Indeed, theoretically, that is completely doable. The observed data log likelihood is the log of the density of the observed data given theta. As you can see, so f of x ops given theta is the marginal distribution of the observed data given theta. So this could involve summation or integration over all possible values of x miss, so all possible values of the missing data, which isn't always straightforward to optimize. In this case, when the complete data log likelihood is easy to optimize, but the observed data log likelihood, which can involve log of some summation or integrations, is harder to maximize. The expectation maximization or the EM algorithm can be quite useful. So here is a brief overview of the procedures of the EM algorithm. The objective is to maximize the observed data log likelihood. And this is done iteratively and alternates between two steps in each iteration. The first step is called an E step. And as you can imagine, E stands for expectation. In the E step, one computes the conditional expectation of the log likelihood of the complete data log likelihood, given the observed data and the current parameter estimate. Let's denote that by theta ode. For now, let's think of theta ode as something that you initialize at the beginning and update it at each iteration. So let's denote this conditional expectation of the log likelihood by Q. So Q of theta and theta ode is equal to the expectation of the complete data log likelihood given the observed data and theta ode. In the case where the missing data, in this case, that's included in bold X, so part of bold X is observed and part of it is missing. In that case, if the missing data is continuous, this is equivalent to the integration over all possible values of X miss, the missing data, of the log likelihood, the complete data log likelihood, times the conditional density that X miss takes the value bold X, given the observed data and the current parameter estimate or the current iteration of theta ode. We'll see more of this when we look at the example. So in the E step, we get this Q. And as you can see, Q is going to be a function that involves theta. So theta is going to be the only variable left inside Q. In the M step, which is the maximization step, we maximize over all possible theta values in the parameter space. This Q we obtained from the last step. And the value of theta that maximizes Q theta theta ode is going to be our new theta. We're going to update theta ode with the new theta we have obtained, and we're going to iterate this until reaching some stopping criterion. For example, until we reach the maximum number of iterations or the change in the likelihood evaluated at 2 consecutive theta odes is less than some preset tolerance level. So before we move on to the example, let me give a few remarks about the EM algorithm. We're not going to talk about the proofs, but under quite general conditions, it can be shown that the sequence of thetas or the theta olds obtained from the EM algorithm is guaranteed to converge to a local maximum. Again, like we talked about when we last week in terms of optimization, most of these methods are designed for finding local instead of global maximums. So if one suspects that there are multiple local maxima, it is advised to run EM with different starting points, in other words, different initial theta olds, and see if they converge to the same value, or if they don't, choose the global maxima out of all local maxima. We're not going to provide a thorough proof for the EM algorithm. So if you're interested in a thorough proof, I included a paper by Jeff Wu from 1983, which is I believe the original paper where they proved that the EM algorithm can converge to a local maximum. But here I will try to provide some ideas on why this method or one iteration of the expectation and maximization cycle can increase the observed data log likelihood. For notational simplicity, so let's no longer write x obs as x obs, but we just write it as x. So x is our observed data, and y is the missing data that we do not observe. Let's note that the observed data likelihood, log likelihood, denoted by L theta given x, the observed data, is equal to the log of the integral over the joint density of x and y given theta over all possible y values. If you multiply and divide inside the integral by this thing in blue, then you can see that this is equal to this. And the second line of equations is essentially equivalent to the natural log of the expectation of this ratio between fxy given theta and fy given x and theta old, conditioning on x and theta old. So this is a conditional expectation. Because this is a expectation, we can apply the Jensen's inequality. Let's note that the log function is a concave function. So by the Jensen's inequality, we have that the log of this expectation is larger than or equal to the expectation of the log. You can verify that the equality holds when theta is equal to theta old. And this is equal to, because this is the expectation of log of a ratio, the expectation of the log of the numerator conditioning on x and theta old minus the expectation of log of the denominator given x and theta old. And I hope this term at the beginning looks familiar to you because this is our old friend q theta and theta old. In other words, the conditional log likelihood and the conditional expectation given the observed data and theta old of the complete data log likelihood. And then you can see that this term in black here actually does not involve theta. So what we have just shown is that the log likelihood of theta given the observed data is greater than or equal to q of theta, theta old, minus this thing, which is a constant over theta. The equality holds at theta equals theta old. So you can see the next theta nu, which maximizes q theta, theta old, guarantees us that q theta nu, theta old is greater than or equal to q theta old, theta old. In other words, by setting the next theta to be equal to the maximizer of this q over here, we will arrive at a log likelihood in the next iteration that's greater than or equal to the current one. In other words, if we implement the EM cycle, our log likelihood, the observed data log likelihood, is bound to be non-decreasing.